So welcome to the seminar on two infinity of class groups. Okay, so the goal of this seminar is to, at least the first three lectures of this seminar will cover the algebraic part of the recent work of Alexander Smith, which was a breakthrough in the subject that I'm going to quickly introduce to you. So we are, the general kind of problems that we are looking at is we look at, we are interested in this family of objects. Say D is a fundamental discriminant that is negative. And the main conjectures one of the main conjectures in this subject, which I will call conjecture 1, goes as follows, and it's not the content of this seminar, but it will motivate conjecture 2. So I fix P and naught prime, P naught prime, and well, the conjectures tells you that if you fix, moreover, a finite abelian P group, then you should have the density of the imaginary quadratic number fields whose p side is isomorphic to A should be inversely proportional to the sides of the automorphism of A. So this is K over Q, imaginary quadratic, so one of these guys there. So I ask, well, the discriminant should go to X. X. And the P part of the class group should be isomorphic to A. So these I mean the P side inside the class group. If I divide out by the collection of such fields, K over Q without the only discriminant up to X. Okay. Then this limit should exist and should be equal to a constant that depends only on C and on P, and you have one over the sides of the automorphism group. Okay, so this conjecture was due to Cohen and Lenstra.
What is the formula for CP? Is it automatic that what CP must be for this to be true? Because
yeah, CP will come back in a moment, and actually will come back in a little bit, and is the product from I1 to infinity of 1 minus 1 over P to the I.
But my question is, suppose that this conjecture is true.
Yeah.
Does it follow that CP must be equal to this product? Does it have to be the sum of the weights?
I'm not so sure that from the fact that the conjecture is true, you can deduce automatically that defines it, because you will need error terms. You would need to sum.
Yes, right.
But you can prove directly that defines the sum over 1 over out converges and converges to that. It's a pleasant exercise. And yes, and I ask here P and odd prime because for P equal to the 2 part of the class group, and this will come back again and again in this seminar, it's a little bit different because we know a little bit more. And I will say later what we know more, but essentially what we know is that the 2 torsion of the class group is in such a manner that this conjecture would never be true. And you will see in a bit what I mean, but let me just state directly conjecture 2, which was proposed by, I think, Gert. So as I mentioned, the reason why people think that the 2 part is different from the P part for P odd is the 2 torsion. So essentially the conjecture is the same conjecture but squaring the group. So fix now A, I use the same A, I hope I can be forgiven for that. 2 group. Then basically the same formula, but you have to substitute everywhere instead of the class group, the square of the class group. Okay, the discriminant goes up to x. And now I ask that 2 times the class group of k to infinity. I'm writing it additively here. So these are like the part of the generated by the squares. Is isomorphic to A. Oh. Okay, literally the same thing. Q imaginary quadratic with discriminant x. This should exist and should be equal to C2, where C2 has the same formula, over the automorphism group. Okay. Okay, so the goal of this seminar is to explain something about this theorem. This is a theorem from last year, due to Smith, which basically says that conjecture 2 is strong. For every finite abelian 2 group, you have the density of imaginary quadratic number field such that the square of the class group is isomorphic to that abelian 2 group is inversely proportional to the sides of the automorphism group of A. And okay, the goal of this lecture is to explain, first of all, to reformulate this conjecture and also then this theorem in a slightly different one, which is still the statement looks different but is equivalent, and to explain a little bit what was done before, and to explain in the second hour I hope to explain the start of the ideas to prove this theorem, and then the next 2 lectures will like keep going on this subject. Okay.
So there is a program for the whole month?
Yes, I think we might be a bit optimistic that we can cover the algebraic part in 3 lectures. And after that, depending also on the interest of the participant, we might explain why the algebraic tools that we are introducing are enough to conclude this theorem.
Okay. And will you also say anything about positive discriminants?
So for positive discriminants, there is an analog of this conjecture, and where you have to replace this by something else. And Peter Koymans has worked out how to fix the main theorem of Smith to get this result.
Oh, okay.
So he might in case we explain how this works for imaginary quadratic, it's up to him to say something for that case.
And is there literature about this?
About which one? About this theorem.
Mm-hmm.
Just literature that refer to this theorem, like Alexander Smith recently proved this theorem. If you go on citation, but there is no literature that uses the ideas of Alexander Smith. I mean, there is no literature that so far.
Okay. So is someone writing this down, these lectures?
What?
Are we writing this down?
Well, I mean, the literature for this theorem, of course, there is a paper I mean, that is written down in a paper, which I think it's probably on the website.
It's an archive.
It's an archive.
A link to the archive page on the seminar webpage.
Yes, but the sort of all the possible things that you can do out of this new thing are work in progress of some people.
Okay.
Yes, for example, you can consider also not only extension of degree 2, but extensions of degree, cyclic extension of degree p, or this kind of question. But okay, let me, so this is like an announcement, and let me go to, so I guess this might be called like section 1.0. Let me go to 1.1. where I want to rephrase this conjecture in a different way, and I call this abstract arcane pairings. So the name maybe is not so appropriate, but I will explain why I call it in this way. Okay, so if you have a finite abelian P group A, so A is now like this, you can write it in such a way. You can assume that it's written in such a way. Where the function fa of I is just a map that is eventually 0, so from z larger equal than 1 to z larger equal than 0, and is eventually 0. Okay? So of course to know A is equivalent to know FA. So A, knowing A is tantamount to knowing f of A. Okay, that is just trivial, but let me rephrase it once more, that knowing f of A is, and then knowing A is tantamount to know all the tails. And let me define that functions. So all the sums of f of A from a given thing to infinity. So knowing f of A is tantamount to knowing a function that I want to call the rank of A. To knowing rank of A. A rank of A is defined as follows. Rank A of I is the sum for j larger equal than I of f of A of I. It's a finite sum because f of A is eventually 0, and this function now is written in a way that is clearly non-increasing. So rank of A is non-increasing, and is eventually 0 as well, and eventually 0. These are trivialities, but they will be useful. And now let me rewrite the function rank of A in a way that, what is this function really? For example, rank of A of 1 is measuring exactly how many pieces I have here. And that you can also measure as the dimension of the p torsion of this group A. And if I want to know rank of A of 2, well, it means that I have to sum from when I have at least p squared here, right? So that means that is the size is the dimension of the p torsion of p times A p squared. So let me write a bit of formulas. Rank A of 1. This is dimension ft of A of p. Rank A of 2 is the dimension over fp of p times A of p squared. And in general, rank A of j is the dimension over fp of p to the j minus 1 times the p to the j torsion. Okay? So that's interesting because now we have rewritten the structure of an abelian group. Well, first as a function, then as another function, and that function as a sequence of dimensions of vector spaces. So that is what we will be looking at. So I will erase this conjecture. Which I hope you internalized. So to know A, is tantamount to know this sequence of vector space, well, the dimension, to know the sequence dimension A, P, squared, and so on, right? Well, and you have an attached, you have a sequence of decreasing vector spaces. You have a sequence of A, P, and these will be the objects we will be working on, but not yet completely, actually. We need one more piece of structure, J, A, J minus 1. Oops. Sorry about that. Thank you. And now what I want to explain next is that the way to pass from such a vector space, there is a secret pairing that is deciding how to pass from a vector space to the next one. And those pairings, that is the title of this section, abstract drafting pairings, will be the thing that we will try to handle. So we will not try to handle like directly the group A. We will try to handle this sequence of vector spaces, or RFP. And what I want to explain now is that there is a pairing that decides how to pass from such a space to the next one. And that is the abstract drafting pairing, and to define it I have to introduce the dual group of A. So this is defined as the of abelian groups, of course, from A to, well, let me write directly QP multi P. Recall that the group AF as a, so maybe I should use a little bit of a better graphic here. So let me put it here. The group AF is easily seen to be isomorphic to the group A, and you have a similar sequence of vector spaces here.
Can I ask something?
Sure.
You say to know A is to know this sequence, but does it really mean, what do you mean to know A? To know A of isomorphism?
The isomorphic class of A. That if
I only need to know these functions, right? I don't need to.
Sure, but if you can, maybe you don't have a way to control the sequence of numbers, but you have a way to control the sequence of vector spaces.
Yeah, but I think there is still a difference between A and that sequence of vector spaces, no?
Yeah, I'm just saying that if somebody tells you all the dimensions of these vector spaces, then you can reconstruct the isomorphism class of A.
Yeah, but
Not futurally.
yeah.
Yeah, okay.
But if I have a homomorphism from an A to a B.
Oh, sure. I'm just. The goal of this thing is determine how often a given abelian group A occurs as the.
Yeah,
okay.
But okay.
Sure, but I think the word tantamount was chosen on purpose because it's not. I didn't say it's equivalent in some precise category. I'm just saying that I can.
So your numbers rho A of I follow from that sequence.
Yes,
Yeah.
that's all I'm saying. That's all I'm saying. But we will be working with the sequence of spaces because they are space. They have more structures.
So I was just wondering how much.
I see.
That's
Oh,
fine.
okay.
Okay.
Okay. So these vector spaces are actually at the same dimension because A and A are isomorphic, and what I want to define is a pairing. Is a pairing at each step of the filtration in such a way that the left and the right kernel of the pairing will be the next vector space in this filtration. So for I in a positive integer, I define a pairing, define art of I of A. So this is a pairing defined as follows: from P to the I minus 1, A Pi times Pi minus 1, A at Pi, and goes in the P torsion of QP mod ZP. And the formula that defines it, it's just the following. You have A here, and you have a chi here. And I say that this goes, and I will explain the symbol that will appear in a moment, into psi of A, where I choose psi, in A at, such that P to the I minus 1 of psi is equal to chi. Let me explain immediately why this makes any sense. So I define now a pairing that I take A here and chi here. Well, at least it's defined at psi in A at such that P to the I minus 1 of psi is chi, because by definition chi lives here. So that object exists, and I can plug in A into psi. But of course the first question is this independent on the choice of psi? Well, yes, because if you choose another psi, remark, if you choose another psi, the main point is that A is also in Pi minus 1, so you will kill the difference basically. So if you change psi, so take psi plus psi 0, well, still it must satisfy this equation. So that means that Pi minus 1 of psi 0 is 0. Well, but then you have that A, if you evaluate psi plus psi 0 in A, well, then this is a psi of A plus P to the I minus 1 psi 0 of B, where B is such that P to the I minus 1 of B is A, and that exists because A is there. Okay, and the claim that I want to make is that this pairing, the left and the right, this defines a pairing, and the left and the right kernel are the next spaces. I erase this theorem.
So instead of chi, you could also have divided A by...
Yes, that was my next, the remark that I wanted to make next. This is a little bit asymmetric as I'm doing, and we will do it in an asymmetric way, because in our setup, this A will be the class group, and that will be the dual class group, and we will have a way to make sense of element of to compare element of the dual class group as the quadratic field varies. But we will not have a way to compare ideal classes. So that's this asymmetry that is in the definition of this pairing that will reflect deeply something that is actually, we will see in this lecture already, that is one of the main ideas of Smith's work, that there is a way to, there is a common ambient space for the element of the dual class group, where you can literally compare them. And I will give a precise meaning to this in about half an hour or so. So yes, this is a bit asymmetric, but from an abstract point of view, as you say, I could have done in the symmetric way. And yeah.
Or half-half.
Yeah, sure, I can, yes. Yeah. So it's more like a proof thing for the application that we decide to define it in this way. And it's defined, it's called actually Artin pairing because later it will literally be, this will be the evaluation of an Artin symbol in some map from a Galois group. So, okay, more in a bit. But let me first state a clear claim that P, I guess I, A, I, P, I plus 1 is left kernel and symmetrically the next one. We write both. Is right kernel. Is right kernel. And both cases of art. Well, this is not, I will not give a proof of this, but this is not very difficult to prove. It's clear one direction is the right, like the computation that we did. Suppose that I have an element here, then when I do this recipe, well, you see that psi is killed by p to the I. So if you find out that A is written as p to the I times b, you find that A kills every chi. So it's clear that this guy and this guy are contained in respectively the left and the right kernel. To show the converse, you have to show that if something is not multiple, you can concoct a character chi in such a way, living here, in such a way that the pairing is not. That is not difficult. I propose that you, if you just go through it and you will see. Okay, so I want now to so we started with A, and we want to understand A, and we said that we have this sequence of vector spaces, and now we have defined an abstract pairing that decides at each step what is the next vector space. So let me restate what is the conjecture of Cohen-Lenstra and of Gert when you rephrase things in this setup. So to do it nicely, let me say that we have a bijection of sets. Yeah, I'm doing all this to arrive at I want to arrive at saying actually what was that Smith proved, because he didn't prove directly the 1 over out. He proved something that looks very different from it. So I'm doing all the intermediate steps. So we have a bijection of sets from finite abelian P groups. Abelian P groups. To non-increasing functions, maps, G going from Z into Z. The bijection is the one that, and eventually 0. Is the one that we, eventually 0, the one that we discussed so far, that sends A into rank of A in I. And now what I want to tell you is what is, I have basically, I didn't prove it, but I told you that there is a natural probability measure. It was asked why it was a probability. It doesn't follow, for example, from the conjecture, but you can show that the formula that we define as Cp over 1 over out defines a probability measure here. Now you have a bijection of sets here, sending an abelian group in its sequence of ranks. And the first step that I want to tell you is to use this description here with the acting pairing to tell you what is the push forward of this measure here on this second set. Because then we will have an equivalent conjecture in terms of this function.